Hi. In this lecture, we're going to spend most of our time talking about landscapes. Now, we're going to use the idea of a landscape both as a metaphor, we're going to think of ourselves as climbing up a landscape, and as a mathematical object, where we map the value of a function at a particular point as an elevation on a landscape. So elevation is going to play the role of function value. I want to start with the simplest landscape imaginable. This is Mount Fuji. Now, if you've never seen Mount Fuji, it looks like a giant pyramid or a cone. And it's relatively easy just by looking to find the highest point on Mount Fuji. In this lecture, we're going to see how some real-world problems from business and from ecology map into Mount Fuji. No, I mean that literally. We're going to literally map real-world problems into Mount Fuji. Now, most of the landscapes we're going to talk about aren't going to be Mount Fuji. They're going to have more peaks and valleys. They're going to look a little bit more like the Appalachian Mountains. Now, these problems are going to be harder to solve than Mount Fuji's because just like it's harder to find the highest point in the Appalachians, there's lots of peaks. There's lots of places where you could get stuck. So if you're standing at some point on the Appalachian Trail, you might see lots of paths pointing upward, and it's just not clear which direction you'd take. Now, the Appalachians are what we're going to call a rugged landscape. So in this lecture, we're going to learn how landscapes become rugged. And the answer is going to be that there's interactions between the variables or choices that an actor takes. So, for example, suppose you're designing a car. If you add weight to the car to make it safer, you might think that makes a better car. But when you do that, the car may be worse because it needs a bigger engine to carry all that weight. So changing one variable to make things better might actually make the overall car worse. Now, people often conflate complex systems with rugged landscapes. They'll say a rugged landscape, a hard problem, is what complexity is. But that's not quite right. So let's think back to our opening lecture. Complex systems involve interdependent, adapting entities. What this means is the value of a solution, the height of a point on the landscape, depends on what other people do. So in landscape terms, this means that you could be standing at some point in some elevation, and then some other actor takes a move, and the landscape literally dances. It goes up or down. So in this lecture, we're going to highlight how, for complexity, it's this combination of interdependence between the entities, people, firms, government, species, and adaptation, them moving around, that cause the landscape to go up and down. Now, throughout, we're going to assume that the entities are connected in some way, and we're also going to assume that these entities are diverse. But to get our bearings, we're going to keep connectedness and diversity at stage left for this lecture, because we just want to get a core understanding of how these landscapes get rugged and also how they dance. Now, in the later lectures, we're going to get back to connectedness and diversity, and we'll get them back into our story. To get an idea of why dancing landscapes are so much more challenging than rugged landscapes, and again, dancing landscapes are what complexity really is. Let's imagine for a second that you're sitting atop a peak in the Appalachian Mountains and there's a rainstorm and you're watching the floodwaters rise. You're going to feel incredibly safe and secure. Now, even though the landscape is rugged, you're going to be at some local peak, you're going to feel fine. Now, suppose an earthquake happens and there's a whole bunch of aftershocks, so the landscape starts to buckle and shift. These tectonic events are going to raise and lower the ground under your feet, literally. So one minute you could be on a summit, the next minute you could be about to be submerged by rising rainwater. Staying dry, staying in a good solution when the landscape dances, requires constant awareness and frequent movement. So these three categories, Mount Fuji landscapes, rugged landscapes like the Appalachians, and dancing landscapes, are the main themes of this lecture. Okay, fine, you might say, but landscapes, I get that. But what is this? How does this have any relevance? Isn't this just all metaphor? Okay, so first, as for relevance, we're going to use these three categories to help us understand why some problems can be solved optimally, both by humans and by evolution, and why others can't. We're also going to see why hard problems, like building an atomic bomb, curing cancer, are not the same thing as complex systems, like markets, ecosystems, ecologies, and international relations. And we're going to see why the best approach to solving a difficult problem, or a rugged landscape problem, differs from the best approach to thriving in a complex world. And so most important in all this is we're going to see how this landscape metaphors, right, this idea of a landscape, lays the foundation for how we can think about complexity. Now, it's not just going to be as metaphor, though, right? Remember, we've got this precise mathematical definition of a landscape. The point in the landscape is basically your action, your solution. And the elevation or is the value of that point. Okay, before we start, we need two definitions. These are intuitive, but they're very important. Now, we all know when we look at a mountain what a peak or a summit is on a landscape. It's just the top of a hill. We want to make a distinction between a local peak, that's just a place on the landscape that if we step to the north, south, east, or west, we'd go down, right? And a global peak. A global peak is going to be the highest of all the local peaks in the landscape. So Mount Fuji, right, just has one local peak, and it's also the global peak. The Appalachians have lots and lots of local peaks. So again, Mount Fuji landscapes are single-peaked, right? And rugged landscapes have lots and lots of peaks. All right. What we want to do is we want to think about how you find a peak on a rugged landscape. Now, if you had lots of time to walk around, or if you could traverse the entire range, then it would be easy for you, right, to find the global peak. But that's typically not going to be the case, right? So you may get stuck on a local peak. Now, when we get to a dancing landscape, we've got a little bit more of a problem. Now, it could be that they have only a single peak like a Mount Fuji, or it could be they have multiple peaks like the Rockies. But the key feature of these dancing landscapes is going to be that they move, they change over time. So if you wanted to stay on the global peak, you're going to have to keep moving. You're going to have to adapt and learn. Now, this idea of a landscape plays a central role in this course. We're going to keep coming back to it throughout. Here's why. In a complex system, agents are constantly adapting locally. These adaptations are attempts to improve performance or payoff. Performance or payoff we can think of as elevation. We're capturing that as elevation. So what we can do is we can think of these agents in a complex system, firms, people, species, as sort of climbing on landscapes, trying to get to local peaks. And if they're lucky, maybe they get to global peaks. But that's not going to be easy to necessarily do. So now that we've got this idea, right, the elevation of a landscape represents how good our choice or an action is. The higher the elevation, the better the solution. We can move beyond metaphor, and we can start doing some real science. First up, Mount Fuji's. One of the points I raised in the opening lecture was that the world has become more complex. Now, the drivers of that complexity have been what? Increased diversity, more connections, greater interdependence, and quicker reaction times, right? You order the milk and they phone the cow. In the past, the core economic, social, and political problems just weren't as complex. That's not to say complexity didn't exist. It's just that we've sort of had this amping up, this ramping up, if you will, of complexity. Let's go back to following World War II. A lot of the problems that we faced at that time were engineering problems. How do we build houses, cars, washing machines, etc.? And if we think back a little bit further to the turn of the 20th century, we see that many of the problems involved manual labor on singular tasks. Laying railroad track, shoveling coal, applying rivets. For these types of problems, a process of trial and error combined with good time management techniques was able to locate optimal solutions. In fact, the insight that experimentation can locate better solutions underpinned an entire approach to doing business that was pioneered in the early 1900s that has come to be called scientific management, or Taylorism, in honor of Frederick Taylor, who was its first great advocate. Henry Ford was one of the people who bought most heavily into Taylorism, and he set in motion something that's been called the efficiency movement. So what did Taylor do exactly? Well, I want to take a famous example of his, and I want to show how this example translates into a Mount Fuji problem. So was this problem the design of an engine or even a light bulb? Nope, simpler than that. It was the shovel. I'm not kidding. Taylor determined the optimal weight for a shovel. So how does he do this? Suppose we start with a shovel with no scoop. So the technical word for this is a stick. If we're trying to shovel coal with a stick, we're going to get zero productivity. So the landscape's going to be very low. Nothing lifted, nothing gained. As we start to make the shovel larger, we can lift more and more coal. Now, the way we're going to measure productivity of the shovel is how much coal an average worker could lift in an 8-hour shift. So as we increase the size of the shovel, productivity increases. So we can think of our landscape as getting taller. But at some point, the shovel becomes too heavy and productivity is going to fall off. And any further increases in the weight of the shovel are going to lower productivity even more. So for example, if we were to make the shovel the size of a kitchen table or this stage, productivity would be down to 0. So what we can do is we can turn this real-world problem into a mathematical function, a graph, and we can think of that graph as a landscape. So what I can do is I can plot the weight of the shovel on the x-axis, the horizontal axis. And I can plot the total amount of coal that someone could lift in an 8-hour shift on the y-axis, the vertical axis. What we see, which we just explained, is the productivity is first going to increase as the weight of the shovel increases, but then it's going to decrease. If we think of this graph as a topographic map, what do we have? We have a two-dimensional Mount Fuji. The slope goes up, reaches a peak, and the slope goes down. A problem like this is easy to solve, a Mount Fuji problem, whether we're doing math or whether we're just on foot. Because in the case of the shovel, all we have to do is keep making the shovel bigger until it gets too heavy, and then we stop. And we're done. We found the peak. By the way, in case you're interested, the optimal weight of a coal shovel is 21 pounds. And it turns out this weight is optimal regardless of what you shovel. This is why snow shovels are bigger than coal shovels. So I've never seen one, but I'm guessing if you went to some factory where they use those styrofoam peanuts, the shovels are probably just enormous. They're huge. Okay? I want to think about the implications of Taylorism in an economy composed of physical laborers. So this is a world of 60, 70 years ago where people apply rivets, they pound nails, they attach doors, they make pies and cakes. In that sort of world, there's a whole bunch of Mount Fuji problems. What that means is scientific management is going to work, and it's going to work well, because it's going to find the global peak on problem after problem after problem. I'm going to just put aside Marxist critiques of this, right? Scientific management, this sort of repetitive labor, is going to be dehumanizing, right? It's not going to be a good way to sort of spend your life applying rivet after rivet, but that's not relevant to our discussion. What's relevant to our discussion is that the world of today is not the world of Taylor. The world of today involves rugged and increasingly dancing landscapes. So that's what we want to go to next. We want to build up to dancing landscapes. But first, we've got to talk about rugged landscapes. So let's recall our mental representation of a rugged landscape. It's a mountain range, like the Appalachians, the Rockies, the Himalayas, that have lots of peaks. Finding the highest point on a rugged landscape isn't easy. The main reason for this is the space of possibilities is huge. It's what we call combinatorically large. Now, this size wouldn't be a problem if we had a topographic map, if we could just pull out the map and say, look, here's the highest point. But we don't. Not only that, we typically can't take leaps anywhere in the space of possibilities. We often are forced to search locally. Leaps, as we'll talk about later in this lecture, often require genius. So evolution is particularly constrained in its movements in this regard. It can't just make these leaps across space. It can't cross tigers with elephants to make tigaphants, which would be some sort of enormous gray beast with black stripes and sharp teeth. So when I say that these things are combinatorically huge, these problems, and we can't make these leaps, what I mean is that there's an enormous number of possible solutions, enormous number of things we could check. So let's suppose you have someone come over for dinner, and they say, boy, what'd you like? And they say, let's have chicken. So you decide, I want to make the best chicken dish in the whole world. How many choices are there? Well, okay, first you got to pick the type of chicken. So you could have free range, corn-fed, gas-fed, grass-fed, right? Then you have to decide what part of the chicken. Is it going to be the leg, breast, back, thigh? Maybe you cook the whole bird. All right, now you got to decide how you're going to cook it. You're going to bake it, fry it, boil it, grill it, slow cook it, right? Or do you maybe just nuke the thing? All right, now once you decide what type and how you're going to cook it, you've got to decide sauce. You can have a rub. Let's say a rub. Let's make it simple. Well, now you open your spice store and you see 50 spices. If you choose 3 of these 50, that gives you 20,000 spice combinations. 20,000. Now we got to decide, okay, what vegetable or grain are we going to serve as an accompaniment? Now, you've got hundreds of choices and literally millions of combinations of choices. So let's multiply all these things together. Number of ways to cook it, number of spices, right? Number of combinations. And what you end up getting is literally billions and billions of possible chicken combinations. All these different combinations translate into lots of places to explore. But having lots of combinations isn't the same thing as being rugged. To being rugged, right? So this just means it's a big landscape. We still haven't got that it's a rugged landscape. To get ruggedness, what we need are interactions. And these interactions are going to make the landscape rugged. Now, these interactions occur within the choices of a single actor. To see how they create peaks, we need to dig a little bit more deeply into an example. And I want to move from cooking the chicken into the idea of remodeling a house, because I think this will hit home with people a little bit more, no pun intended. So let's suppose I have a house that's got a small entryway, and I decide I'm going to expand this entryway. Seems like a good idea. But when I expand the entryway, what happens is I have to wipe out this bedroom closet. So what I thought was a good move, a move up on the landscape, has made the house worse, because now there's no closet in the bedroom. So it turns out maybe the original design was a local peak, and I just stepped off it. But, let's not give up. We can keep moving forward. So let's just add another closet to the bedroom. Well, that seems great. But it turns out if I do this, maybe I have to wall over a window, so now the bedroom's too dark. So again, attempts to move up in the landscape have made me worse off. We're slipping in elevation. And the reason we're slipping in elevation is these interaction between variables. Now, you could say, wait, let's just add a window to the bedroom. And if we do that, we have a better entryway, we've got a closet, we've got a well-lit bedroom. Everything's right with the world. Okay, let's ignore the fact that we spent $10,000 making this better. Let that go. Thing is, we had to make a whole bunch of changes to get off one local peak to get to another one. So to go up, we had to go down. It's because these choices interact that getting to a higher peak requires multiple changes, right? Entryway, closet, window. So here's the simple rule. The more interactions, the more rugged the landscape. So the problem, the optimal size of the shovel isn't connected to anything. There's no interactions except what's being shoveled, so that problem's simple. Decisions in the home remodel are all interconnected. They're all interacting, and they're connected to various systems, electrical, plumbing, etc., so the landscape is rugged. Now, the problem of evolving species is a classic rugged landscape problem. Suppose we wanted to improve the human. I mean, we seem pretty good, but we've got some problems. One thing we might want is we want a blowhole in the top of our head, because then we couldn't choke, and we'd get fewer diseases. But how would we do that? We can't just drill a hole right through the center of our brain. That's not going to be so easy, right? So that decision would interact with other parts of our physiology. Now, as difficult as rugged landscape problems can be, they're not complex. They're not complex because they're fixed. They stay the same. Ruggedness is often a component of complexity, but to get complexity, what we need is we need the landscapes to dance. To explain the difference between a rugged landscape and a dancing landscape, I'm going to describe two problems that seem very similar. The first is going to involve a milk distributor, and the second, an airline. Okay, so first the milk distributor. Each day, cows produce milk, farmers harvest the milk, and the distributor goes and picks it up, pasteurizes it, and then deliver it to different stores. Now, assuming that demand at these stores stays about the same and the cows produce about the same amount of milk, the distributor just has two problems to solve. First, which trucks to send to which farms, and then once it's pasteurized the milk, which trucks to send to which stores. Now, it wants to do this in such a way as to maximize profits. This isn't an easy problem. It's a rugged landscape, in fact. Why? Because shifting one farm from one route to another route may lower the cost to reassigning another farm, a neighboring farm, to that route as well. So finding the optimal solution to this problem is really difficult, and computer scientists have spent a lot of time and use a lot of computational power trying to solve them. What's relevant for us, though, is the problem, as hard as it may be, stays fixed. The farms aren't changing location, the cows aren't moving around, so it's the same rugged landscape day after day after day. Let's consider an airline, though. It has a similar problem. It has to decide where and when to route its planes. And it's got to do this in such a way to maximize profits. Now, this profit landscape is also rugged. Shifting one flight may require changing other flights. What differs, though, is the airline's landscape dances. It dances because when other actors change their behavior, the airline's profits, and hence its landscape, changes too. There's interdependencies between the actors. Okay, who are these other actors? First, there's the consumers. Adding a route, say Chicago to Hamburg, Germany, may increase demand on a whole host of flights to Hamburg, and then by necessity to Chicago. This doesn't happen for the milk, right? When the milk distributor adds a new stop, say a new farm, milk from the other farms doesn't line up and say, oh wait, we want to get on the truck so we can go to this new farm. Second, the other airlines also affect the landscape. When they shift or add a route, they alter our airline's profits. Now let's suppose you're running an airline. So what you do is you decide, we got to solve this problem. We got to figure out how to route our planes. So let's hire some really bright statisticians, mathematicians, computer scientists, maybe even economists. We'll put these brilliant minds to work for months, and they're going to figure out the perfect set of routes and prices that give us the maximum profits. So they figure all this out, and we decide on June 10th, we're going to implement these changes. You wake up on June 9th, and you see that a competing airline has implemented a whole new set of routes and prices. So they've completely changed where they're routing their planes. Turns out it too had hired statisticians, mathematicians, and computer scientists. But it moved first. What does that mean? It means that the problem that we just spent, the rugged landscape that we just spent 6 months trying to solve, it's gone. Poof, it's just gone. The landscape has danced. There's been like a tectonic shift, right? Mountains have gone up and down. Hills rise where there were once valleys. Peaks sink to the floor. So what was once a good solution may not be a good solution. Let's go back to our house example. It's as though you spent months formulating an ideal renovation of your house, only to wake up on the morning construction's going to begin and find someone's replaced your house with an entirely different house. So once there was a hallway, now there's a den. Once where your kitchen was, there's now a bathroom. Oh, and by the way, you've now got a screen porch. That's what I mean when I say life on a dancing, rugged landscape is complex. So here's the subtlety, and it's a really important one. What makes a landscape rugged are interactions between our own choices. We saw that in the case of designing the house. What makes a landscape dance and a situation complex are interdependencies between our actions and the actions of others. So when one player's payoff, one actor's payoff, right, the height of their landscape depends on the actions of another one, that's an interdependency. That's an interdependency. Those interdependencies only come into play when other actors are adapting, if they move. So complexity requires both interdependence, their actions affect ours, and adaptation. Note also that just as increasing the number of interactions increases ruggedness, increasing the number of interdependencies increases complexity, though only up to a point, as we're going to see in the next lecture. Your world, your daily life would be much easier if landscapes would stay fixed, but they don't. And because they don't, it's not necessarily the case that people, governments, firms, organizations, or even species are always doing the optimal thing. Sometimes they're doing the thing that used to be optimal, but no longer is. To borrow a phrase from Charles Lindblom, a political scientist, people are muddling through. Okay, quick summary. We've thrown out a bunch of ideas here, and I just want to get our bearings. You can think of the potential solution to a problem as an elevation on a landscape. And if we numbered those solutions, let's say from like 1 to n, we plotted their values, in some cases we get a Mount Fuji. That's going to be an easy problem, and we just climb to the top and hold up our 21-pound shovel. But when our choices interact, which is the case when designing a house or routing the milk distributor, we get a rugged landscape. We get something that looks like the Appalachians or the Rockies. Now finally, if our payoffs depend not only on our own actions, but the actions of other people, we get a dancing landscape. And a dancing landscape requires these interdependencies and adaptations. All right, so keep this straight. Interactions between an individual make the landscape rugged. Interdependencies between people make the landscape dance. So then you might ask, who cares? Why does all this stuff matter? First, seeing the distinction between a Mount Fuji landscape and a rugged landscape helps us understand why sometimes evolution or human systems can locate optimal solutions, the 21-pound shovel, and why sometimes they don't. So suppose you're out in the field and you look at the face of a sunflower. You're going to see a tight spiral of seeds. Now as the sunflower grows, these seeds sort of attach themselves sequentially, starting from the center and spiraling outward. So you can think of, metaphorically, think of a tractor just driving out from the center of the pod head and dropping seeds at some distance. Now we can measure these at an angle, right? Because the tractor's driving in circles. That angle in a sunflower is approximately 137.5 degrees. So think of the hands of a clock at 10:15. Now, suppose you ask yourself the question, suppose I want to pack as many seeds as I could into the head of a sunflower. So I'm going to begin at the center of the seed and sort of spiral out. What should that angle be? How often should I drop a seed? Well, the answer turns out to be 137.5 degrees. Well, that's sort of amazing. Let's see why that's true. Suppose the angle were 90 degrees. If every 90 degrees you dropped a seed, then what you'd get is you'd get 4 straight lines starting up from the center of the power. You drop one at noon, you drop one at 3, you drop one at 6, you drop one at 9. Then you do that again, one at noon, one at 3, one at 6, one at 9. You want to avoid piling up seeds at the same angle. So the way to do that is to choose an angle that's an irrational number. Now the math here is very complicated, but the trick is to choose an angle proportional to something known as the golden mean, which is approximately 137.5 degrees. This is something that mathematicians figured out. But here's what's just incredible. Evolution figured this out as well. So how did evolution solve this? Okay, well, let's think about it. Early on, sunflowers didn't break out a chalkboard and prove some theorems about exactly what the golden mean is or what this angle should be. There was no Taylor in the world of sunflowers. What happened is sunflowers evolved with different angles for seed placement. So as the angle got closer to 137 degrees, they could pack in more seeds, which meant more flowers. But once they went past 137.5 degrees, this led to fewer seeds and therefore fewer flowers. So in other words, if you think of the angle as the horizontal axis, what we get in the packing seed problem is a Mount Fuji landscape, a single peak problem. So it's not at all surprising that evolution could figure this thing out. If we contrast the seed packing problem with the problem of designing a house, well, the house problem is more rugged. That's why architects keep coming up with new and better houses, because the landscape there is rugged. Designing a house requires lots of choices, and those choices interact. Hillary conquered Everest, that's true, but the perfect house has yet to be built. Falling Water by Frank Lloyd Wright notwithstanding. Now, the distinction between fixed and dancing landscapes has massive implications for how we allocate resources. Building an atomic bomb, as hard as that was, was a rugged landscape problem. The landscape didn't start to dance until after the bomb got dropped. Regardless of who struts and frets upon the stage, a bomb is a bomb is a bomb. Therefore, the government could solve this problem by doing what? By squirreling away brilliant physicists in the mountains of New Mexico and letting them just go at it, right? The landscape was going to stay fixed. Yes, it was rugged, but it was not going to dance. If you have a rugged landscape problem like building a bomb, it makes a lot of sense to devote serious resources for a long time. Let's cure cancer. Let's build a more efficient and safer nuclear power plant. Those are rugged landscape problems. But once the landscape starts to dance, it makes a lot less sense to devote too many resources or spend too much time. Why? Because time is of the essence. As soon as you start trying to solve the problem, it may move. This is one reason why government panels to reform Social Security or to overhaul the tax code come up with recommendations in a few months rather than a few years. If problems change quickly, so must solutions. In the case of the Manhattan Project building the bomb, if the landscape had been dancing, the physicists could not have been tucked away. They'd have been better suited in, well, Manhattan, right in the seat of the action. That's true for most modern knowledge workers. We're all toiling on a dancing landscape. The closer a person is to the action, the more she's aware of the changes in the landscape. That's just one of the many reasons workers in larger cities are more productive on average than workers in rural areas. They're more aware of how the landscape is moving. A final and most intriguing insight that comes from this landscape idea relates to what philosophers call standpoint and what we commonly call perspectives. What I'm going to say next is going to sound a lot like a phrase from some sort of New Age deconstructionist Zen Buddhist. And it's an idea I introduced in a book I wrote a couple years ago.